That's how you waste time. Hey guys, welcome to another episode of This Is Your Lab. I'm your host, Dr. T, and today we have Alex. He knows this experiment pretty well. He's done it before in the past. In today's lab, we're going to be going over centripetal force and its role in circular motion. We'll be studying how centripetal forces actually act towards the center of a circular pathway and confirming that the acceleration is centripetal, and we're going to confirm that there's a relationship between centripetal force, the tangential speed of an object going in a circular pathway, and the radius of that circular pathway overall. But before we do, let's go ahead and talk about today's pre-lab. For today's pre-lab, you're going to test the theory. Is it really centrifugal force or centripetal force? Is there an outward force or is there an inward force? Newton's second law. Remember that the direction of acceleration is the same as the direction of the force. So what we're going to do is use the Firefox app. We're going to go back into acceleration without G, as we've been using. And this time, you want to hold the phone exactly as you would be chit-chatting with a friend or, FaceTiming or what have you. Make sure that your Y orientation is outward from your hand and X is going towards your thumb. That means Z coming out of your palm. Once you're confirmed in that configuration, you will push play, slowly move into position up here, hold for a few moments, and then slowly bring back down. Once you pause the data, you should be able to very easily confirm which axis underwent the most acceleration. If you weren't able to analyze your experiment right after you took it, you can save the experiment state, come back to it a little bit later. It'll show up as blue listed objects. You see I've got centripetal acceleration from that experiment you just watched. And here we are. Now remember that the orientation of the phone is very critical in that case. You held the phone in such a way that you moved in an arc with the y-axis pointing outwardly. If centrifugal force is a real force, then the acceleration should be positive. But if centrifugal force is fake and centripetal force is the thing, then our acceleration should be negative. Now, this is just noise along the z-axis. There's something going on with the x-axis. That's true because we accelerated going up and down moving our hands, but we're more interested in the y-axis. So let's zoom in on that. And this time, you take this picture. This will be the one. When you zoom in there, we don't need anything else, but you want to stay within there. You can see the zero, you can see the maximum accelerations, but this is very clearly a negative acceleration because the bottom of your phone, and make sure your orientations are good when you do it, the bottom of your phone was pointing towards your own person, acting as the line of centripetal force, and that the acceleration was pointing towards your center of person. You zoom in a bit, make sure you keep a little bit that shows that it was zero otherwise, and print this. Just to be on the safe side, you can save your experimental state in this case and come back to it later. We already done that. If you'd like to see how far you did go to more tools. You can look for the linear fit, and it will put a line up here, and then you pick your data and you touch right here at the point and you draw a line to the highest point. It'll tell you. Because it's acceleration versus time, we're looking at the maximum difference. That's minus 41 meters per second. You can also zoom this out further and see that you're out at 64 meters per second squared at your as your maximum when you're swinging through. Once you have your data and you've satisfied demonstrating that your acceleration was negative, centripetal acceleration does point towards the body, go ahead and capture your picture and transfer it to your laptop or whatever, and edit it, put it into Microsoft Paint, hit that inverse colors if you've got that. If you can't do that, go to the website that's made available on D2L, and you can invert that color so it goes easier on your easier printing at that same case. So that's using this exercise to confirm centripetal acceleration for your pre-lab. So the topic that we're entering into, circular motion, may seem a little bit uneasy, bizarre, peculiar, because we've been working with straight lines so far, and now we're getting into circular motion, and the variables are different, the equations seem to be a little bit new, but consider the possibility that they may actually be more similar than you expect. Let's take, for instance, the concept of arc length. If I want to measure an arc length on this ball, for example, from this point to this point, I would take a string, lay it across, and that will be the length here, this distance across the edge of the circle to one point, from one point to another. And if you think about this as a circle with a center, then this is at some radius, and this is some angle distance that is carved out between one point and the other. We refer to this as arc length. And if we take this string and we lay it across a meter stick, we can measure the linear length to that. And so the relationship between arc length and the angle and the radius is given by the direct relationship S equals r theta, where S is a linear quantity, r is a linear quantity, angle is an angular quantity. Well, just as we can do with a position, a change of position will be a velocity, so distance over time, v, is equal to r. The radius doesn't change for a circle, but the angular position can change, and we refer to that as angular displacement or angular speed. And then linear acceleration would be related to angular acceleration, again by a ratio of the radius of the circle, or circular path, if you will. So I've got written up here for you the linear qualities and the angular qualities, and when you put them side by side, you can actually see that they actually mirror each other very nicely. You have linear displacement, linear speed or velocity, angular speed, also angular velocity, but the angle is always in that angular direction. So we don't talk about the vector quality quite as much. It is there, but because it's all going in one direction, or the reverse of that, it's kind of redundant. It doesn't tell us anything new. Linear acceleration, angular acceleration. And just for clarification, just to kind of help you navigate the letters, this is the Greek letter theta. This is the Greek letter omega, not a W, but it's similar to a W, but you kind of write it a little bit different. And then the alpha, like an A, you can just make it look like an X that you don't lift the pen off the page. So that's the letters that we're working with right now. You see the linear kinematic equations are familiar. Well, when you make the substitution of these quantities into your linear kinematic equations, the radius drops out, and you end up with identical forms with just using the angular quantities, theta, omega, and alpha. So now that we have taken a look at circular motion itself, the basics of the motion, and shown that the kinematic equations are very directly related to the linear kinematic equations, let's talk about Newton's laws. At least in particular Newton's second law, because as you can see, Newton's first law would prefer you go in a straight line. Remember, Newton's first law says an object in motion, which we assume is a straight line motion, an object in a straight line motion continues in that way unless acted upon by an external unbalanced force. So here's our mass that we have tied to some string that's going around a circle. Well, the simple fact that it wants to go in a straight line, that's Newton's first law, that's the concept of inertia. And so the mass wants to go in a straight line. The string, however, prevents that from happening. Let's explore what that means. So this mass difference here, this means that the path is changing. It can be going the same speed, but if the path is changing, that too corresponds to a changing vector, and a changing vector is enough for us to qualify for acceleration. So let's take a look at the acceleration concepts here. Newton's second law, written straightforward, F equals ma. In this case, we're going to consider just the one force that's causing it to change motion, where the single force acting on a single mass undergoing circular motion is going to accelerate somehow. How do we accelerate it? Well, the relationship that is not derived right now, but you should have access to, at least through resources I've made available to you. Centripetal acceleration can be described as the tangential speed, the speed at that surface point, at that point in time, squared, which makes it now a scalar quantity, over r. Again, r is the radius of the circular pathway. So we substitute that in, we get centripetal force defined as mv squared over r. Now, formally, we would write it in this way. If force is a vector, mass v squared over r, these are all scalar quantities, but it's still a vector force, so we have to represent that with an r hat. If you've done the x hat and the y hat in lecture, that simply means that x hat is a vector that goes in this direction along the x-axis, and it's only a unit vector. Its length is 1, which means that all it does is point that direction. The y hat goes vertically, goes along the y-axis, again, unit vector of length 1, so that it doesn't change anything, it just shows you the direction. So an r vector, r hat vector, would be pointing outward anywhere from this center point. Now in this case, it's positive, always positive. There's no such thing as a negative r hat vector. Everything originates from the center of your point where that vector originates. always pointing outward. So when you see here, the force vector is equal to negative r hat, that means that the force vector is pointing inward towards the center at that point on the circle. But this is something you contemplate. Just think about it. But as far as practice and what you're going to do, this is the one you want to remember. This just kind of background information. This is the guy. Okay, so now that we've looked at Newton's second law as a centripetal force, a force acting inwardly causing the object to go in a circular pathway, we can now apply these circular quantities and obtain the force using an angular measurement. So we start with Newton's second law, mv squared over r, but we know, okay, wait a minute, linear speed is related to angular speed by the radius, so if we square that, we get v squared equals r squared omega squared. We substitute that in, the radii simplify, and your centripetal force can be written in this format, where instead of a linear velocity and radius, we're now looking at the angular speed and radius, and it's a linear relationship, there's no fractions involved. So your task in this lab is going to be to compare the centripetal force that you measure using this relationship and the hanger force, which is the mass of the hanger times 9.8. The centripetal force apparatus is this big, mean-looking contraption that you can see here. It's a large, heavy base. This base has been placed specifically by the teaching assistants and the lab instructor, so please make sure that you don't dislodge or displace it from its current position. It is balanced according to its current position on the table. The object moves very freely, and you want to make sure when it's balanced, it should not move anytime you place it to a new location. It consists of the base, a photo gate, which you will see is just similar to the pulleys. It has gaps that are evenly spaced that Pascal knows how far apart they are. On top of this rotating arm is the rotating platform, at the center of which is a center post. The center post you see has a spring, an orange indicator disc. It has an adjustable indicator bracket. The top support is also adjustable. The string is tied to the indicator disc, which goes through a hole, fed around a pulley, and connects to this centripetal mass itself, suspended by a string aboard this side post assembly. The centripetal mass has 3 hooks for the various string connections. The mass is about 200 grams, which you will confirm using a scale. You'll attach a pulley, you'll feed one of the hanger masses over top of it, and then begin your analysis from there. In this configuration, we want this assembly to rotate, spin around, but before we do so, we've got to make sure that it's aligned to represent where the centripetal mass is going to be when the centripetal force acting towards the center is equal to the hanging force that's coming this way. To do that, you notice that the string here and the vertical line on this are not in full alignment, and so we can adjust this a couple different ways. We can adjust the radius. For part A, we'll keep the hanging force a constant, and for part B, we'll hold the radius constant. So we can adjust this left and right, but even then, and we like it to be in a position where this is not a terribly stretched string. When the spring is completely stretched, we're reaching the limits of its flexibility. So we can adjust this to some space where it's not quite so stressed, and then adjust until that's about as lined up as we can get it. And we can, for further adjustment, we can move this ever so slightly up or down to get more accuracy. We're almost there. This line is now lined up. In order to be sure that this line is lined up with our vertical in such a way that all forces are canceled, vertical and gravity, centripetal force, and the hanging mass force are all in balance, Newton's first law, and letting us to say, okay, the centripetal force acting on this object is going to be equivalent to the hanging force. We want to make sure that this pink disc is easily recognizable mark. So we adjust this down like so. There are different ways to do it. I'm going to align it to be flush, the flat surface of the top of the disc, flush with the flat surface of the top of the bracket. One thing to be sure of once you have it in this configuration is that this is fairly horizontal. This side's a little bit less
requiring of it because the tension of the force pulling this way is going to be governed by the spring action. But on this side, this should be very horizontal. Otherwise, you've got components of the hanging force and not the hanging force that's holding this vertically and opposing whatever the centripetal force configuration setup is here. So make sure that this is level, and you can adjust the height if you need to in order to accomplish that and see if that helps reduce your error. This is now ready to rotate, except we need to now take off the hanging mass and the hanger and the pulley. So take this off, disconnect these, set these out of the way. You should note that the indicator disc is now sitting above relaxed spring from the bracket. And now we're going to rotate this and bring those into alignment and keep it as a line flush with the surface as we can during our 10 seconds of data collection. First thing that we'll do when we get into Capstone is the usual. We go over to this guy here, and we're looking for on the 50 the port in which we place it. In this case, I've placed it in the fourth port, so we'll click on that. And because of the spokes that are on the rotating platform, this will behave like a photo gate with pulley. So we click on photo gate with pulley, and we want to set our decimal places to give our few extra ones. We want angular speed, radians per second. So we'll turn that up about 2 extra decimal places. So get that to 4. We don't need quite as many as usual. Time, we're going to boost that all the way up as usual to 7. And then we'll grab a graph. We'll set it over here on the right hand side. Doesn't need to be the entire screen. We just want to have something that kind of lets us know what's going on during that motion. We'll take angular speed versus time preset, and then we're going to grab a table and drag it over to the side here. And the time is largely irrelevant, but we want the angular speed to run. And then we're going to click on the sigma. That will turn on, if you notice down at the bottom, min, max, mean, and standard deviation. We're only interested in mean, but if you only have the mean turned on, then it may be difficult to notice as the last line and the rest of this is data, especially when it's coming in live. If you are interested in turning that on or off, you can go up to the drop list and select whichever measurements you want. But we're interested in the mean over the period of time of interest. So this data is ready to collect. So we begin recording, wait a few moments. Once it's begun time, again, this is pulley activated, so you notice that data is not yet started collecting because this is not started moving. You have to be careful not to block or let anything give you erroneous blocking of your picket fence except for the pulley wheel or the flagged wheel here. So, and rotating it using just your fingertips, increasing speed, and you'll notice that your data is going up. And you want to be careful because this will bounce, and you want to just be very gentle with it. Right now I'm a little bit below it, so I'm actually faster speed than it needs to be. So I'm going to do a gentle move, and then we'll mark time once I get out of control. All right, here we go. So we're trying to keep it around this speed for 10 seconds. It's mostly staying good. Little tiny gentle motions, and that should do it. Stop. And now you can see in here, we've got a range where the data was largely under control. You can see in the data, we've got a high speed, and then it drops down low where the disk was sitting right above the thing. And then this period right around between 55 and 65 seconds is largely where I had it under control. So we turn on a highlighter for that region, like so. And you'll notice that it highlights the selected region in your table. And this will give us the mean. It's 2.7811 over here on the left. You can also show that on the table here, on the graph here. And you'll record this as your angular speed into the table, your radius that you have measured into the table, these values, mr omega squared, mass being the mass of the centripetal force. Then you can compare it to the hanging force by percent error, because this is a pretty well understood mass and it's fairly well machined, consistently machined. We can use it as a reference point for easier calculation and say, well, we're pretty sure that this was good.
So that's today's lab activity. I'd like to thank Alex for joining us, helping us out, and going through the process. So we'll see you in the lab. Thanks. Okay. Well, that sums up today's lab activity. Hopefully, I always say hopefully. So that's today's lab activity. I hope it's. I keep doing that. Stop it. This is not a promotion. What do you think? That's good? Okay, so for today's pre-lab, you're going to test. You're going to chest.